the suspend logic that you have up here,
Microphone is set up.
which Andrew is trying to use, we're trying to use.
Okay.
Here.
Mr. Neely, I apologize. I'm going to start recording a thing. That's okay. I guess I don't need my video. You don't need to see the back of my head while I'm doing this. All right, here we go. It's that time. It's review time again. So we're here with kinematics. This is going to be our first review session. Today, we're going to try to focus on kinematics and a little bit of forces as we move through our different units here. So the goal today is going to be, we're doing our first unit, but our review is going to be kind of structured similarly for all of these different units. The first thing we're going to look at is in kinematics is we're going to try to identify some key relationships and equations. Some of these are going to be things you already know. Some of these are going to be things that you might need to be reminded of. The biggest single issue that people tend to have on the exam is they can throw any topic at you. So one question you always want to ask yourself is, how do I know when it's a kinematics question versus an energy question or a rotation question or a forces question? And then reminding ourselves how to select the right kinematics equation or use a graph. So we're going to go do an overview. We're going to look at some key equations. We're going to get an opportunity to look at some of the multiple choice questions from the packet and kind of answer some questions or go over a few of those specifically. And then if we have a little bit of time, I have a totally separate practice FRQ that's all about kinematics that we can talk through if we want. All right. So let's kind of start by reminding ourselves of kinematics. This is going all the way back to late August and September and everything. So we got our kinematics equations, right? We remember all of these things. There are three kinematics equations that I want us to think about. They give all of these on your formula sheet, which is nice. Well, almost all of them. So we've got our first equation. Remember, this one tells us, I guess philosophically, the big thing with kinematics is obsessed with how things change over time. Specifically, how position, velocity, and acceleration are related over time. Let me move this bar somewhere where it'll be a little less obtrusive. How position, velocity, and acceleration are related over time. In general, in like the broadest sense of the word, we want to think about those calculus definitions, right? That if I've got position or displacement, if I want the velocity, what I'm doing is I'm taking a derivative or maybe looking at a slope of a graph. If I've got a velocity and I want acceleration, I'm taking another derivative to go down. And then if I want to build myself back up that ladder, I'm taking integrals. In the broadest sense of what we're doing in kinematics, we're doing derivatives and integrals. Now, a lot of the time, we don't actually do derivatives and integrals. A lot of times we can rely on our kinematics equations. And the most important thing to remember about our kinematics equations is they only work for constant acceleration. If your acceleration is changing, if they give you a function of time or your acceleration is non-constant because it like your car is going at one acceleration and then changes acceleration, you can't use your kinematics equations. You might be able to use them for like a piece individually, bless you, but you're going to have to go back to calculus. That said, there's a lot of cases where the acceleration is constant, and then we've got our kinematics equations. Our first kinematics equation tells us how, these are all obsessed with change. It tells us how velocity changes with time. If I've got some acceleration, it tells me what my velocity will be at some later date. Maybe I've got two different velocities and we can figure out the relationship between acceleration and time. But that first one tells us how velocity changes with time. Our second one really tells us how position changes with time. Yes, it's got initial velocity and it's got acceleration in there, but it's really sort of telling us if we know our velocity and our acceleration, where am I going to be at some later date? Well, of course, you could also use this in other ways to like solve for other parts of that equation. The third one, and I want to remind you, the third one is sort of secretly not a kinematics equation, but you can still use it. Really tells us how velocity changes with position, how position and velocity are related. This one is really useful because there's no time in it. And you'll find in a lot of questions that time is either missing or you just don't have easy access to it, or it takes you too long to find. And so in cases where you don't really care about the time, you can shortcut it by using that third kinematics equation. I do want to note, there's a secret fourth kinematics equation, which can be rendered like this. We talked about it a little bit differently in the start of the class. We noted that the average velocity, and I want to remind you that in general, average velocity is total displacement over total time. In the case of constant acceleration, average velocity is also the average of the initial and final velocities. This can be really, really, really handy because it tells me maybe I'm in a sports car or whatever, and I start off at 0 meters per second and I get up to 30 meters per second. My average speed for that interval is going to be 15 meters per second. So it can be a really handy way to quickly calculate distances or things without having to 1/2 AT squared or whatever. That really only applies for constant acceleration. It tends to fool people a little bit, so be a little cautious about using it, but it can be a lifesaver in certain circumstances.
What's the fourth one, Shane?
This fourth one is also about position versus time. It's a little bit of a different way to state the second kinematics equation. They've just played around with the it's instead of using acceleration, it's using initial and final velocities in this case. So that can be a very handy one. The biggest key to kinematics, I think, if you've identified it's a kinematics problem, is thinking about what you have and what you need. If you can figure out which quantities you have, it's going to lead, and what you need, it's going to lead you to the right equation. If you decide that you say have an initial velocity, a final velocity, and a distance, and you're looking for an acceleration, you can be like, oh, well, I've got two velocities, a distance, I want an acceleration. Time doesn't factor into here. My third kinematics equation has two velocities, a distance, and an acceleration. It links those things together. So if you can figure out what you have and what you need, one of those kinematics equations is going to link those things together. Great. There's a particular case in kinematics that comes up all the time. We did a whole thing on it, which is 2D motion, and specifically a thing called projectile motion. So 2D motion more generally, the key to it in kinematics is you can actually take apart the x motion and the y motion. You can consider the x motion separate from the y motion. And you can do that. That's very, very handy. When you're doing that, you're using all the same kinematics equations. Make sure that you're only setting up your equations in one direction. So if you're using that first kinematics equation in the y direction, make sure that you're only using y velocities and y acceleration. Don't tell me that gravity is going in the x direction, right? So if you're doing a y equation, only use y quantities. If you're doing an x equation, only use x quantities. The only thing that gets to play in both x and y is time. Projectile motion is a very special case where our only acceleration is in the y direction. It's gravity, it's always down. It's nice and constant, it's a constant number. And as a result, the acceleration in the x direction is constant. Or excuse me, it is constant, it's 0. The acceleration in the x direction is 0, which tells us that our x velocity is constant. So if you track this thing over the course of its motion, that x velocity never, ever, ever changes. It's the y velocity that reduces and then eventually goes back down. The y velocity changes, but the x velocity doesn't. There are a few really helpful points and things to remember for projectile motion. Possibly the most important is to remember what happens at the very tip top, the very apex of our flight. What happens at the top of our flight? Yeah, the y velocity is 0. Please note the y velocity is 0. That's supposed to say what that says Vy, not Vg. The y velocity is 0 right at the top. Notice that the y acceleration is not 0. It's still accelerating down. It's just momentarily stopped. There's a few helpful little key equations here. I particularly like to find the time for something to go up using that first kinematics equation by just saying, well, if I throw something up in the air, how long does it take to go up? Well, I know that it starts out at some initial y velocity. I know that it ends at 0 velocity at the top. And I know that its acceleration is negative g. So you can figure out the time that it takes to get to the top by just doing y velocity divided by g, which is awfully helpful. When things are going back down, I often find that using 1/2 AT squared is a little bit easier, but really you can do it in a wide variety of different ways. The keys to remember here are that the y velocity is 0 at the apex. That's a really helpful point to fix on. And that your motion in the x direction is incredibly simple. Your motion in the x direction is just speed times time. The motion in the x direction is totally and perfectly constant. How do you know when it's a kinematics question? This tends to throw people because like kinematics gets sprinkled in all over the place. The biggest single key is that it involves time, especially if you're given distance, velocity, or acceleration. Now, occasionally time can be other things. Time can be momentum or impulse. Time can be power or something. But a lot of times when they're asking you, how long does this take? Hey, what's going on at t equals 3? A lot of times you can fall back on kinematics. Kinematics is obsessed with time. If there's no time in the question, maybe it's a third kinematics equation, or maybe you're looking at it somewhere else. Another key, if it's projectile motion or free fall, if things are launched or thrown or are falling, a lot of times it's projectile motion. Of course, obviously, energy and some other things can come in there as well. Another key to kinematics is often none of our kinematics equations don't involve mass. So if there's no mass involved, a lot of times that might be a sign that it's kinematics. Now, there are exceptions. Sometimes they might give you a force, and then you got to use F equals ma to find the acceleration. And then from then on, it's a kinematics problem. But if there's no mass in a question, sometimes it's a clue that they're looking for kinematics.
Do they ever do like the shockers, like they put the mass in and actually need it?
They'll sometimes give you the mass when it's not needed, but sometimes they will very pointedly not give you the mass and are expecting you either to set up an equation where it cancels out or to find a kinematics or other approach to it.
Right.
So like here are some past FRQs that are good examples. Here we've got a little object that gets launched off the ground and then it collides with the box. So the first half of this question is kinematics up until the moment where it collides. And then once it collides, what are you going to do?
Conservation of momentum.
Yes, excellent. Momentum, right? Once it collides, you get momentum, and then it swings up, which might be and stops, which might be an energy. It might be an energy thing. So you've got a couple different phases to that one here. This is a rotation question, which I used to give on the rotation exam, where a cylinder rolls down a ramp and off a table. So the first half of this is a rotation question. They love to do this on the exam. Oh, here's a rotation question. A cylinder is rolling down the table, 1/2 I omega squared, all that good stuff. And then it falls off the table and it's a projectile motion question. So a lot of times they'll just tack projectile motion on at the beginning or the end to make sure you can do it. Occasionally it's disguised a little bit differently. Here we've got a 100-kilogram box pulled along the x-axis. The box slides across a rough surface, and they give you a position function. Hey, here's another clue that it might be a kinematics equation. They give you position as a function of time, right? They're asking you for the speed of the box. Oh, we should probably go ahead and take some derivatives, right? So these are 3 examples of past FRQs that used kinematics as a big part of it. All right, so what we're going to do is I want us to take a couple minutes. I'm going to pause the recording. I want us to take a couple minutes and kind of look through some of those multiple choice questions. If there's ones we want to go over, I've got actually a couple on here. Actually, let's take a moment. I want you to look specifically at 4 and 5, just because I've got it pulled up. Maybe you've already done them. I want you to look specifically at 4 and 5. So take a couple minutes, look at 4 and 5, and then we're going to talk about them. Not that the other ones aren't. All right, so what do we have? We've got sweet basil, cilantro. No, it's different questions. Yeah, cilantro's got to be right.
Secondary issues of taking down.
You want me to grab the book, or do you have it?
What?
What do you need to vote?
Oh, I'm used to like trying to do the first problem.
Okay.
Remember, you have to do like the linear to.
Mhm. Great. All right, C1 here, C2 gets you something.
Use this that first.
Where do we get 3 from?
Okay. Multiply E times the I was hiding.
So let's be a little careful. C2 is this one. Remember the tell me. C2 is this part of the curve, right? Where X is equal to 1. Y is equal to T, right? So like, we want those about. If we go here, let's do that. That was so big.
Oh, no, I threw it off and I was waiting on that. I didn't think of the same sticker.
I know it's.
Yeah, oh. Yeah. And you. You didn't get it out. I know you want it.
They have nice available.
You get to big lick and you want that.
Minus 2. Well,
Is that not negative velocity? It's just goes back to a certain.
Wait, you're talking about one, no, but one, so at.
Yeah.
Oh, yeah, did I just go back to start?
that's.
Usually the four is.
I hate to do.
What is now is acceleration.
Andres, take a look at the parameterization for three curves. But I think we're getting mixed up about
Velocity.
the
So, but.
X and Y. Yeah, so, yeah, I mean, you can do them in any order, right? Doesn't matter. We gotta do
The constant.
we're making a closed loop around there, so we want to do 3 lines in a row.
Not zero. A has returned.
I'm multiple except doesn't have to be she was kind of shocked as well. If there is
Gee, isn't it possible to say
accommodation
B could move in some weird,
even like a
like,
5 functions.
weird acceleration?
Because sometimes
like
I
non-constant?
couldn't
it be like an
look at
What I'm gonna tell you is, I'll ask is.
Do we really know it's?
I didn't
Answer
think so.
probably not. You also don't have to simplify your answers. If you wanna leave it as big, messy, like. The square root of 7 squared plus 6 squared plus 3 squared, just leave it.
The last question, that's that everybody's because it's definitely, A is definitely.
Yeah. I would leave them.
It is constant, it's just, it's.
Arithmetic is the thing that happens, but like, I would be,
It's just a zero. It's not. Accelerated.
I would. Yeah,
But it's not.
I will ask, but I'm not optimistic about that. All right. Let's take a look at 4 and 5 here. So we got, whenever you see a graph, and this is the thing with Ms. Shrek beat into your heads, which is the moment you see a graph, what's the very first thing you should look at? Yeah, look at the axes. What is it graphing? So we've got time and velocity. Great. It's showing us the velocity as a function of time. And the moment we've got a velocity versus time graph, we know we're kind of in the middle with velocity. So if we need to talk about acceleration, we're going to take a derivative. If we need to talk about position or displacement, we're going to do, we're going to do an integral. We're going to talk about area. So it asks, at what time x equals 0 does the car first pass through its starting position? Excellent. So we're doing some kind of area integral stuff here. So let's think about what happens to this Hot Wheels car. What's happening during that first second?
Down by.
Yeah, it goes backwards, right? At first it's speeding up backwards. And then what's it doing? Slowing down backwards. So at first it speeds up and then it slows down. And at 1 second, it stopped again. But as Jillian said, it's moved. If you look at the area under here, it's moved negative half a meter backwards, right? And then it starts to pick up some positive velocity and it starts to go forward, right? At some point, it's going to get back to its starting point. How far forward does it have to go to get back to its starting point? 1/2 a meter. What if I go all the way, looking at my traces, what if I go all the way to 2 seconds? Yeah, this is going to be,
Probably someone.
yeah, so careful on the scale on the graphs. The scale on the graphs can be a little weird. This is 1/2, which means it's got an area of 1. Oh, I went too far. And if I went too far, that means that I hit 0 where?
In between.
In between 1 and 2. So I hit 0 somewhere in between 1 and 2 seconds. Excellent. All right, what if I wanted to know the total displacement of the Hot Wheels car over these 4 seconds? Well, I gotta keep going. So that was 1. This box is gonna be 2. This box is also gonna be 1. So I get +4 minus 1/2 gives me
I thought displacement includes.
displacement. So distance would include, distance would be, doesn't have a sign. Displacement is like displacement is final minus initial. So it ends up, if we kind of imagine that it starts at x equals 0, it goes backwards and ends up at, it goes back 1/2 a meter, then forward 4 meters. So it ends up 3.5 meters from where it started. Yeah. So total displacement. Yeah?
Yeah.
All right. Are there any other ones? I've got another one pulled up, but are there any other ones that we were maybe glancing at that looked?
You did.
3? Yes. So let's go ahead and take a look at this. I should probably pull open this this packet. I should have had it open to begin with. So let's go ahead and get. Do I already have a? Nope, I don't already have it.
I think I know it, but we all seem to.
Great. I love disagreement.
You said it was. Oh,
Wait.
when you said 2, was it?
2 is impossible to say,
And I-
right?
Um,
Right. How do you know how do you know it's
Because
possible?
if you look at it.
I've got
Yeah, but that's just looking at it.
Yeah.
a mechanics packet here. Hold on, let's actually, we can actually just go ahead and look at that first, this first chunk here. And yep, grab all 3 of these. All right, we got object A, object B. All right, so if we're looking at object A and object B, which one's the furthest from the origin? Which one has the largest displacement in those 2 seconds?
B.
B. Absolutely. What does the displacement of A look like?
Like. You.
Yeah, so it goes.
How does it have a straight line? How does it just?
Yes, okay, in real life, this is not realistic because it's changing speed infinitely fast. In reality, there would be some slope to that line. But we sometimes have idealized graphs here. If something did move like that, it would suddenly chunk back to going backwards and end up back where it started. All right, which object moves with constant non-zero acceleration?
I said A.
I say neither.
No.
Okay, impossible. I say it.
Well, A has no acceleration.
All right.
There's no slope.
All right, if you had a,
It's not A.
well, so, all right, so if I think about, let me think about sketching an acceleration graph for object A, which is a little bit of a strange beast, right? At first, we have a flat constant velocity graph, so our acceleration is 0. And then also for a while over here, our acceleration is 0. But what about that brief moment in the middle? There's a huge negative acceleration. It would spike down really quickly as we descend. It can't. I guess put more simply, our velocity changes, so there has to be some kind of acceleration, right? So it can't be object A. Object B looks nice and smooth. Smooth. If it's got constant acceleration, what should our velocity graph look like? It should be a line, right? This might have a constant derivative of acceleration, but this one, right, this sort of looks parabolic. If I think about my acceleration my acceleration is changing with time, right?
What? Okay, the derivative of this isn't a straight line.
The derivative of that could be a straight line. We don't really know. The problem is, even if this is a straight line, an acceleration graph that goes like this means our acceleration is changing,
Okay.
right? Our acceleration is changing, and so we want an acceleration that never changes. So as far as I'm concerned, neither of them have.
What? Well, I thought it was impossible to say. I thought for B it could be technically.
Absolutely not. The slope of this thing is constantly changing, right? This is velocity. If my acceleration is constant, this has to have a constant derivative. Does this have a constant derivative?
I guess.
Oh, you guess not? Is the slope here the same as the slope here, Thomas? No, the derivative is changing, and so the acceleration can't be constant. It could have a linearly changing acceleration, but that's not constant.
Isn't that like?
If you want to double check.
Yeah, the jerk would be constant.
Yeah.
No. All right, so then going to number 3, which one plausibly has returned home after 2 seconds? A has returned home after 2 seconds. A has returned home after 2 seconds. Yeah. Well, so imagine that our acceleration, let's just think about that. Imagine that our acceleration looks like that, right? I don't know, it's 3, right? What would the velocity graph of constant acceleration look like?
See how it's nice and straight and just says
Yeah, that's constant acceleration, or this, or
I guess we're thinking
That-
about constantly increasing.
that's different. This acceleration is constantly increasing, but it's definitely not constant. If I have a constant amount of money in my bank account, it means that I have $3 today and $3 tomorrow. I would like a constantly actually, I would like an exponentially increasing amount, but I'll settle for constantly increasing.
Maybe a little bit 14 as well.
Definitely go, it's the 14th best question there is.
So it's like at the, it's not a very good question.
Probably middle of the pack, no, 14, we got. All right,
Well, there's only, no, there's like. Dang, there's a lot of them.
well, in this section, there's like 20 something, 26, I think. All right, so let's take a look at a target. So we got a target lying flat on the ground, 3 meters from the side of a building. We would like to roll a ball off to perfectly hit the target. And we want to know what's that initial perfectly horizontal velocity that we need, that it won't let me write on the board for some reason. What's that perfectly horizontal initial velocity that we need in order to hit our target? We're going to go a little overkill for this question. One thing that can be very handy for projectile motion questions, especially if you're feeling any discomfort, is to create a little table of what you know in each direction. So tell me, what's something that we know? All right, we know which part should I put that on? Y. So I'm going to put my y acceleration is going to be -g. As a reminder, you can use -10 everywhere you want on the exam, and most of the multiple choice questions, unless otherwise stated, will be using 10. The free response can be a little bit different, but if you use 10, you're going to be, if they tell you what to use that. Otherwise, 10 is.
Our
It's good.
initial velocity is 0.
In which direction?
X.
We actually are looking for initial x velocity, because it's going to come off that cliff horizontally.
Oh, Y.
Initial one.
Yeah, our initial y velocity is definitely 0. We also do know our x acceleration, which is going to be
It's gonna be 6.
0, right? Okay. We also know a few other things. We know our delta x and our delta y. Right?
We know our delta X.
Yeah. How far away is the target? 3 meters.
But you don't have to start it from.
Well, that's just going to roll along. No, you don't know how far back it's. We just know it's 3 meters from when it starts to fall. And our delta y, I guess if I want to make my acceleration -10, I should make this be nice and make this -10 also. But if you put a distance of 10, you're going to also do that. All right. So we got all of our bits set up. I want an x velocity. Let's see if I can just get it. The nice thing about my x direction rate is there's no acceleration. So if I set up my second kinematics equation, I can do delta x equals, right, v0 x. I don't know why I put that not in the subscript. V0 x times t plus 1/2 ax t squared. The nice thing, of course, is what's my acceleration?
Would you have to do X initial, we just call it zero?
Yeah, I mean, and that's what I put the delta x in. Slide over. My acceleration is 0. So remember, my motion in the x direction is very, very, very straightforward. It's just v0 x times t. And what that tells me, okay, great, I got 3 meters here. Wait, I have a problem. I need to find the time. Now, once I find the time, I just do 3 divided by the time and I'm there. Cool. Well, I've used every bit of information I have in the x direction. So maybe we should try the y direction. All right, let's take a look at this. I've got an acceleration, I've got an initial velocity, I've got a distance, and I want a time. Do we have a kinematics equation that links those 4 things? Yeah, the second one, right? The second one. No, that's fine. You said it correctly.
That's just the 1/2
Yeah.
t squared.
1/2 AT squared. Now, if we go ahead and write that in the y direction, we can go ahead and write delta y equals, again, I'm going to just do this all the way out because it's been a while since we've done this. AYT squared. The nice thing here is we know that our initial y velocity is nothing, right? If I want to be really responsible here, it falls down 10 meters. This is 1/2 -10 t squared. Of course, if I've got a negative on both sides, I can just make it positive. So I've got 10 meters equals 5 t squared. T squared is going to be 2. So how long does it take to hit the ground? It takes for 2 seconds to hit the ground. Which means what velocity do I need? 3 over root 2 meters per second. There we go. Yeah. We do 30. Oh yeah. No, that's going back. We can't go back. Price is right rules.
I've
That's
seen the prices.
what?
I've never seen.
That's. I don't know whether it's good anymore. All right. Let's take a look at. Let's go back one. Let's take a look at 13. One thing that you're going to find very helpful, especially on the multiple choice, is if they don't give you a picture, and I gotta be honest, they're actually pretty decent generally about giving you pictures. If they don't give you a picture, sketch yourself a little picture in the sidebar of the test. So let's actually do that together. What should I draw? A little clip. I don't know how tall the clip is. So we're gonna, let's just,
H.
yeah, H, perfect. It's not a driver, it's a diver.
Oh.
This is not where they're not Thelma and Louising it. We'll draw a little water. So here we've got a diver. They're going to they're diving. They dive off with an initial speed of v, and they land in the water a distance d from the base of the cliff. And then the question is, how far from the base of the cliff would the diver land if they had a speed of 2v? We're going to tackle this one very accurately. But let's also start with, are there any answers that we think are less likely to be correct?
Probably A.
Probably A. We might suspect that if you're going faster when you fall off the cliff, you will go further. Probably a good thing to do. So let's actually think that d is a distance in the x direction, right? How are we going to calculate our distance in the x direction for projectile motion? Yeah, it's the second one. But of course, it's important to remember the acceleration in the x direction is
0.
0.
So it's just D is, oh, that's one of them.
D is just going to be v times time. Now, we know that our speed is doubled. So the real question here is, what's happening to the time that it takes for the diver to hit the water?
It's squared, right? For the, you find it in the water.
Oh, wait, no, this is in time.
Because the Y isn't changing.
It is totally unchanged. The diver hits the water in the exact same amount of time, because time is a function here. Where's the water? It's down, right? It's in the Y direction. The Y motion of the diver is totally unchanged. Initial Y velocity is the same, height's the same, gravity is the same. Everything in the Y direction is the same. So the time it takes is unchanged. All we've done is doubled the speed, and so what did we do to our distance? We doubled the distance. Now, of course, this would be a little bit of a different question. What if we doubled the height of the cliff? Yeah. If I double the height of the cliff, it'll increase the time by how much?
Or two?
By √2. It'll increase it. If you think about height equals 1/2 GT squared in the Y direction,
Oh,
our time will be √2h over g. That h is in the square root. If I double the h, I only get √2 more time. Part of that is because even though I'm going twice as far, think about, I fall the first distance, that second half of the cliff, I'm already going real fast as I'm falling down, right? So I cover that second half a lot faster than I covered the first half. If I wanted to double the time, I would actually need a cliff that's 4 times.
Yes.
That's too high a cliff. You shouldn't jump off a cliff that's 4 times that high.
What is the original height?
We don't know. That's that. Yeah.
1 inch.
I jump off of 4 inch.
I would also do that.
If you guys ever did when you walk downstairs.
That's such a good
Yeah,
one.
Which actually should make you think, if you've ever seen a cartoon where somebody like drops something or jumps and then somebody runs down the stairs to catch it, you can't go down the stairs faster than if something falls. Because you're just sort of controllably falling from step to step.
Unless you're a cartoon.
You could like push yourself down.
You would have, you could like shove yourself down on the handrails. Sure, at that point you get some additional downward force.
Should you drop like?
Okay, if there's air resistance, that's sure, but like, yeah.
Or just being a cartoon.
Being a cartoon has other upsides and downsides. All right, I did want to take a look at one other question before I give you a few more minutes to look at some things here, which is I actually wanted to look at these last 2 questions in the kinematics section, because it's an example of an unusual type of question that they ask once in a while. And it is a thing that they cover. I know they cover it in BC calculus. I also know that they cover it in multi. It's not exactly polar. It's parametrics. It's parametrics. So if you've never done something like this before, what we're getting is the x position and y position as functions of time. So if I plug in a time t, I can figure out where my particle is, right? I can figure out where my particle is. So this gives us the position. Let's try to think about this just intuitively without knowing anything else about parametrics. Maybe you've never studied them. Some of you I know have. They're asking us about the speed of the particle. All right. Well, let's think about what this particle is doing, right?
Speed, velocity without direction.
It is. It's the magnitude of the velocity. All right. So let's think about this particle. Which way is it moving?
Doesn't matter.
Well, we don't have a particular time, but what I guess I'm saying is its x position changing?
Yeah.
Yeah. Could we, for instance, find an x velocity?
Yeah.
How would we do so? We could take a derivative, all right?
It's negative
We get
15.
-15 sine 3t.
But if
Okay.
we're going counterclockwise because the Y is.
Depends on what. Yeah, it depends on what time it is. We will be going. It will be going around like that. So it's got an x velocity. Maybe its x velocity is that way. I don't know. Right. All right. Could it possibly have a y velocity?
Yeah.
Yeah, possibly. What y velocity could it have?
15 cosine.
15 cosine.
So that's
Okay.
so it's 0. It's not.
So it could have some y velocity. If I want, okay, let's say it's x velocity is that way and its y velocity is that way. Which way is its total velocity?
It's not moving.
Why is
I mean,
it?
They're
Square root one plus.
Why-
Oh, cosine and sine are different. That's-
Also, we're not going to add them up directly, right? We're going to the total velocity is gonna be that way, right? If it's moving to the right and up, then it's moving up and to the right. How could I, for instance, find the magnitude of this third side of the triangle of this thing? Yeah.
That's not great.
Use the Pythagorean theorem. So let's figure out this speed. Let's figure out speed, which is the magnitude of the velocity. I'm gonna take a square root. I'm gonna do a little thing here. When I square these, I'm not gonna bother to do. I'm just gonna leave this as 15 squared. 15 squared sine squared 3t plus 15 squared cosine squared 3t. And here's where we get to have that fun magic of what's sine squared plus cosine squared? 1. Please be careful. This is not equal to 1. It's equal to, right? Something sine squared plus something cosine squared gives you that thing, right? Like, a sine squared plus a cosine squared. If I factor that out, I get a sine squared plus cosine squared. And that's where I get just that coefficient remains. So, and then that cancels. So what's its speed? 15.
Why are there, and like, what mistake could people make that makes it oscillate?
They might look at the sine and cosine and they want to say, because what this object is doing is it's going to be going around in a circle. And if you look at the individual velocities, right? The individual velocities go from positive 15 to negative 15, right? Sometimes it's going that way, sometimes it's going this way. The individual velocities oscillate around, but the total speed remains constant.
I think I'm gonna just say this. How come when you do the Pythagorean theorem, you square it with it as well as?
And you square the whole thing, right?
So you're distributing the.
Yeah, I'm distributing the square rather than,
The minus just doesn't matter because.
well, it's squared, yeah.
For the sine squared plus cosine squared, it was just sine plus cosine is so on, or
Not regular sine plus regular cosine, it's gotta be squared. Sine squared plus cosine squared equals 1 is like one of those ironclad trig things that's like,
Are these graded?
they will be, yes, you should. Yeah. I would like them done. And I will reward you with points for it. I will also release a key before the exam. What I want to know, how long does it take for the particle to go once around the circle? So we could try to do something like that. Let's see if we can be a little bit cleverer about it. Let's see if we can remember a thing that we know about. Let's see if we can remember a thing that we know about sine and cosine function. Notice that it's cosine 3t and sine.
Is the radius 3? I think it's petals. The radius is.
The radius is 5. It's not petals in this case.
Yeah.
What do we remember about sines? Normally sine and cosine takes what to do a period? 2 pi. When I multiply it by 3, does that make my period longer or shorter? It squishes it up by a factor of 3. So if I want to make my period shorter by a factor of 3, it's going to be 2 pi.
Wow.
Over 3.
Wait, period is just seconds? Period is time?
Period is time. So one of the other things to remember is when we did simple harmonic motion, right? We had like cosine omega t, and that omega was 2 pi over t. That's also true for just regular sine and cosine functions. If we actually look at this thing, you can pull up parametrics and Desmos, and if you know one thing about me, it should be that I love Desmos. 5 cosine.
Desmos is the best website. Yeah.
It is in fact the best website.
Sine squared plus cosine squared is one for some reason.
I can even do 5
Then it became.
cosine 3a,
Maybe even need to do anything.
5 sine 3a. So if I kind of look at this thing,
Yeah.
what my particle is going to do,
Like a.
yeah, it's not actually going to bounce back. That's just
think each other crazy.
That'll be fun though.
There you go. It's just gonna keep going. Go around and around and around, and you can see after 2 pi/3, it gets back to the middle. Why 2 pi/3? Well, if I plug 2 pi/3 in for t, I multiply by 3 and I get 2 pi, which means I'm back where I started. It just does it 3 times faster. So every so often they do ask these kinds of 2D parametric questions, and you can fall back on some calculus things. One thing that is helpful is basically anytime in the exam they give you something that it looks like escaped from calculus class, they probably want you to do calculus too.
Can you also find a circumference and divide that?
That's another thing you could do. Let's say you're like, oh, I don't know what's going on here, but I'm pretty sure that the radius is 5, right? I'm pretty sure that the radius is 5. All right, my radius is 5. If I want to go once around the circle, what's my circumference? 2 pi r, right? So my circumference is going to be 10 pi. So what if I tried to find time by doing distance over speed, right? What if I did, I have to go 10 pi. I know that it takes me 15 seconds to do that.
That's not mine. Is it mine?
I'm just going,
I think it's going from the roof.
No, it's over there.
we'll all get that done.
Maybe we'll call back. If it was important, we'll call back.
If I do distance over time, I in fact get 2 pi/3.
Wait, how is that not a rose? That's so.
That's you're thinking of r equals. You're thinking of like r equals cosine 3t.
Oh.
This is just x and y individually.
That's
Yeah.
crazy.
This is x and y individually.
Mr. Bates,
Yeah.
What, like, even if it's a polar, you can have like 3t, like, should it be in theta, or do you think you just still do t?
In this case, it's as a function of time. So it's yeah. It would be theta if it were polar. This is parametrics as a function of time. So
Oh, but like, oh.
Yeah. they did that in BC, right? That's one of the BC stuff.
Yeah, we do polar, but we also have data.
Oh, but they also do parametrics though.
Yeah, we do.
Earlier. Now we're doing polar, so everyone's looking at it and like.
You just haven't thought about it in a while.
Yeah.
Well, if you're taking multi next year, we do a bunch of parametrics.
Whoa. I'm taking basic next year.
It's gonna be good stuff. All right. So normally I'd be able to stay long. We got about 25 minutes because I have to be able to eat or I will die. Before class. Do you want to talk about forces or do we want to just take some time and work on the kinematics part of the packet? We can definitely talk about forces.
Then, packet.
Will we
Awesome. No, we'll still do forces. It'll be okay. I'm not gonna rush things. All right. In that case, we're gonna pause the video here for those of you who are joining us online. Farewell. So long, farewell.